Good morning, everyone. Myself Sakshi Mittal. I am Assistant Professor in EC Department, Ajay Kumar Garg Engineering College. And today I am going to record a lecture on topic Location Principle of GPS for subject Satellite Communication KEC 062. So first thing, before going to the location principle of GPS, we must know what is a GPS. So GPS has revealed it is nothing but a global positioning satellite system. So we have launched a satellite specifically for the purpose of locating a target, and it has revolutionized the navigation and principal location. Originally, it was launched for the military purpose, and now it is the primary means of navigation for most of the ships, aircrafts, and widely used in surveying and many other applications. GPS was originally named as Navstar, and it was developed for the military navigation system for guiding missiles, ships, aircrafts to their targets. Now, how we will locate our target? So, these GPS satellites, they used to transmit the L-band signals that are modulated by several codes. So, the first one is the CA code, the coarse equation code, and these codes, they are made available to the public in mid-1980s. First one is the C by A code. Second code is the high security P codes. They allows authorized users. These are mainly intended for the military purpose only. And these P codes, they are the one which allows you to achieve a position accuracy up to 3 meters. So this was the accuracy that military users wanted to target a bomb or a cruise missile, because for in military purpose, we need very accurate accuracy, or the location which we are just tracking, it should be accurate. So the first commercial use was in surveying, but by 1980, several companies, they have produced the low cost handheld GPS receivers like the one we are having in our mobile phones. We can be located, and these days many applications have also been launched that you can have an application and you can just locate your dear and near ones. So they are now available as a low cost handheld GPS receivers. Increased sales and large volume production quickly brought down the price of GPS receiver, and the market have expanded rapidly. So now these GPS receivers, they are now a consumer product and they can be found in every car, your mobile phone. There are other position location systems also, such as your LoRaN, and that can provide you the location of the target, but with less accuracy and reliability as compared to the GPS. So the success of GPS is an excellent example of what the satellites can do. That is, there is application. So that is the broadcasting. So unlimited number of GPS receivers, they can operate simultaneously, because all that a GPS receiver has to do to locate itself is to receive signals from 4 GPS satellites. That means if I have got a target, then particular target that have to receive the signals from the 4 satellites. Obviously, it can receive from multiple satellites. So this GPS space segment, it consists of 24 satellites launched in the medium orbit at an altitude of around 20,000 km with an inclination of around 55 degree. So the satellites are clustered in groups. We call it as a constellation of 4 satellites, and each constellation is separated by 60 degree. As the satellites are launched in the medium Earth orbit, so their orbital period is approximately half of one sidereal day. As in the geostationary orbit, we used to have a full sidereal day, the orbital period. In case of medium Earth orbit, we have the half of sidereal day. That means the satellites will appear in the same position in sky twice a day. Like this shows the example of a GPS, how we used to launch the GPS satellite over the in the space. And it is just such that it is above the Earth at around 20,000 km. The orbits of 24 GPS satellites ensure that anytime, anywhere in the world, a GPS receiver can pick up signal from at least 4 satellites. That means minimum 4 satellites are required to locate a target. If I have got a signal from less than 4 satellites, then it is not possible to locate a target with the signal from 4 satellites. So I require a 4th one satellite also. And maximum, it can be up to 10 satellites can be visible at some time, and more than 4 satellites are visible nearly all the time. As I have already mentioned that in this GPS space segment, 24 satellites are launched at a time. We have 6 standby satellites, so that makes a total of 30 satellites are available, and you want to receive a signal minimum from the 4 satellites. Maximum you can receive signal from 10 satellites. And why we need those 6 standby satellites? So because the replacement satellites, if we need to replace anything, if the satellite's lifetime is over, or if any of the component is degraded, then you need the replacement satellite. So that for that purpose, we need around 6 satellites. So that makes a total of 30 satellites in a space segment. Now, how we locate it? So we call it as a trilateration. So the distance of the unknown point from 3 known points is measured, and so I have got a target here. My 3 sources, for example, we'll take an example. I have a target here, for example, this is the target. This target, it should receive signal from 3 satellites in space. That means it should also send a signal, this should also signal, this should also send a signal. Now, if 3 satellites are sending me a signal, how will I locate it? See, when a satellite is transmitting a signal, I say that it is transmitting the light waves. As and when a light wave is reflected back, that means it has gone to an object, that is your GPS receiver, it strikes it and it is reflected back. So the distance the light waves travel from satellite to the GPS receiver and then to go back, that is the round trip. That is the twice the distance. I know the velocity at which light waves travel. Then we have observed the time, how much time it has taken to reach the GPS receiver. So if you know the time, you know the velocity, but you can calculate the distance. So the distance can be easily measured by finding the time, how much time it takes for a pulse to travel between the two, the satellite and the GPS receiver. So, to achieve a position accuracy of 1 meter, timing measurements must have an accuracy better than 3 nanoseconds. That means when you are transmitting a signal from a satellite and you are saying that you got 3 satellites which are transmitting a signal to the receiver, they are transmitting the pulse waves. That means the timing, they must have a clock which is highly accurate. So the satellites, they carry the highly accurate atomic clocks and they radiate a sequence of bits that starts at a precisely known time. So all the clocks in the satellites, they are calibrated clocks. A GPS receiver contains a clock that is synchronized in turn to the clock on each satellite that it is receiving. Otherwise, how much time if the clocks are not synchronized, it is not, we cannot find the intersection of the intersection point for the signals of 3 satellites. So the receiver measures the time delay of the arrival of bit sequence, which is proportional to the distance between the satellite and the GPS receiver. Now, when the distance of a GPS receiver from 3 satellites has been measured, then the remaining information that is required is the position of each satellite. So, we have launched the satellites for locating a target. That means their position we already know. It's just that the satellite is not stationary, they keep on moving. So, we need to update their location every let's say every few seconds or every few minutes. You need to update their information, that is where the satellites are there located. So their position we already know. We have to locate the position of a GPS receiver, and that position we have calculated assuming that the 3 satellites have sent a signal, they have been reflected back. So wherever those signals will intersect, we call that it is the location of that GPS receiver. So, since the time at which the transmitted bit sequence started, it is known at the receiver, the position of satellite can be calculated from its orbital data. So, as I have already mentioned in the previous slide, that the position of satellite we already know. So, from its orbital table, or we can say the FMRIS data. So, the FMRIS table is nothing but it carries the information related to a position of a satellite. So, they already, it's like a lookup table. So, these information are already updated. So, we can just check from that and we can know the position of a satellite. So, GPS receiver can know the position of a satellite, which satellite is sending signals. Then, making the calculation of 4 satellites provides the receiver with sufficient information to determine its position with very good accuracy. 4 satellites rather than 3 are needed. Why these 3 satellites are needed? As I need the information in 3 coordinates. So, for that purpose, I need the 3 satellites. The 4th satellite is needed for the timing error. If I have got any timing error, for that purpose, I need 4 satellites. Now there are 4 unknowns. That means if there are 4 unknowns, I must have 4 equations to solve that, so that I can get the 4 parameters. Now, these GPS satellite, they transmit 2 signals at different frequencies. First one is the L1 and then is the L2. So, the L2 signal is modulated with 10.3 megabit per second pseudorandom PN bit sequence. It is nothing but a random bit sequence. And it is used by military positioning systems. So, P code is in an encrypted form. It is also known as the Y code. So, I have encrypted the P code and it is now being known as the Y code. And it restricts the use of P code to authorized users only. It is generally for the military purpose only, and it is not available for the civilians. The L1 frequency carrier is modulated by 1.023 Mbps, and we call it as a C by A code. So, P codes, they are modulated at 10.23 megabit per second. C by A codes, course equation codes, they are available for the public use and they are modulated at 1.023 Mbps. So, the higher bit rate of this P code, it provides better measurement accuracy as compared to your C by A codes. So, P, that's why P stands for the precise, it gives you the precise accuracy. So, the GPS systems which use this secure Y code, or you can say the encrypted P code, they require C by A code. So, they provide 2 kinds of service. First is the precise positioning service and another one is the standard positioning service. In case of precise positioning service, you will track both P code and C by A code on L1 and L2 frequencies, and this precise will give you almost accurate position. So, it is mainly used by the military users, and this standard positioning service, it tracks only the C by A code on the L1 frequency. So, it is not that accurate as compared to your precise positioning service, which it is. So, that is why it is available for the general public, and PPS, because it is tracking it very accurately, so it is available for the military purpose, because that is a crucial zone actually. So, P, or you can say the Y codes and the C by A codes, they are transmitted by each satellite. It creates a direct sequence bit spectrum signals which occupy the same frequency bands. Both C by A and P codes are made publicly available, but P codes cannot be recovered in a GPS receiver without knowledge of the Y code. So, see, we are saying that both the signals, they will be transmitted, but if you have knowledge about this encryption, how you have encrypted the P code, you have the knowledge about the Y code, then only you will be able to decrypt that information and you can just receive the signal. So, this Y code is generally made available to the military users only. They can just retrieve the information. So, that is why we say that they have got a very precise accuracy. So, the basic requirement is that there must be 4 satellites transmitting suitably coded signals, your C by A and P codes, and 3 satellites are provided to provide the distance measurement, and the 4th one to remove your clock error. Now, the 3 satellites, they provide the distance information, like they may your measurement of range from the satellite to the receiver, and the 4th one, so how can you now calculate this range Ri? So, each distance Ri can be thought of as the radius of a sphere with GPS operating at its center. Then the receiver lies at the intersection of 3 such spheres. So, see in this, if I have got 4 satellites, so the first one, it is transmitting a signal, second one, third one and fourth one. So, I am saying, I assume this satellite, it is located at the center of a sphere. So, how it will radiate the signals? It will radiate the signals like in a plane. For example, if I have received the signals like these, the arcs, second one will also transmit you somewhere arc, third will also transmit an arc. So, we are saying the 4th one also will transmit an because it should be in the sphere form. So, wherever you find that these spheres have intersect, that defines the position of a GPS location. Obviously, if I have got a sphere, if I have got it as a sphere, that means they will intersect at some other point also. It's not that they will intersect only in front of a plane, they will intersect out of the plane also. So, there will be 2 intersection points. So, we generally ignore that point which is out of the plane, and the point which of the intersection which is in front plane, we call it as a location of the GPS receiver. So the basic principle is the intersection of 3 points completely defines a point. Thus, 3 satellites, through measurement of their distance to the receiver, they define the receiver location close to the Earth's surface. So there is also another point in the outer space which you generally eliminate in the calculation process. So GPS satellites carry 4 atomic clocks which are calibrated against time standards in the GPS control stations around the world. So the result is GPS time, a time standard that is available in every satellite. Now about these highly atomic clocks. So their accuracy, it's like 1 part in 10 to the power 11. So it is too expensive to include a atomic clock in most of the GPS receivers. So a standard crystal oscillator with half accuracy, that is about 1 in 10 to the power 5 or 1 in 10 to the power 6, it is used instead. The receiver clock is allowed to have an offset related to the GPS satellite clock. So when a time delay measurement is made, the measurements will have an error caused by the clock offset. Now, if we know that the satellites, they are located at the center of the sphere and they are just, we want to know the intersection point. So I'll have 3, I need to frame the equations for that purpose. So we'll have the receiver coordinates designated by ux, uy and uz, and the 4th satellite, for the 4th satellite will have coordinate like the x1, y1, zi. So if it is for satellite 1, x1, y1, x2, y2 and so on. So we'll see the equations. Now see, these are the planes. So if I'll just complete it, it will form a sphere like this manner. Same way, this is also it is radiating in a spherical manner. So wherever these will intersect, like it is intersected here in this plane, so we call it as it is the location of my GPS receiver. So the distance from first satellite to the GPS receiver designated by R1, from satellite 2 to receiver R2, satellite 3 to the receiver R3, and the 4th one is, it will be R4. So how we'll make the equations now? So the distance between the 2 points in coordinate geometry is given by r square equals to distance between those 2 coordinates in x-axis, y-axis and z-axis. So we got the 4 ranging equations as x1 is the x coordinate of the satellite minus x coordinate of your GPS receiver. This is unknown. y1, this position point of y coordinate of the satellite we already know. uy is the position point for the GPS receiver, again an unknown. z1 is the 3rd coordinate of satellite and uz is again an unknown. So we've got 3 unknowns. Same way, from all the 4 satellites I can frame equation x2 minus ux, y2 minus uy, z2 minus uz and so on. Now how we will equate this? So this is actually the range. Now this range, it will be equated with the timing. So we call this PR, it is the pseudo range. So I know the pseudo range and we are subtracting this offset error, this bias from every pseudo range. So the pseudo range will be different because all the satellites, they are at different points. So the pseudo range or their range from satellite to the receiver, it will be different. So now I have just subtracted the bias, the timing error from these, and after solving these, we can have the we'll get to know about the 4 unknown parameters. I will solve them. Ux, uy, uz, ux, uy, and your uz. It will define the location or the position for a GPS receiver, and 3rd one is the offset error. So this c is the velocity, and about the tau, we'll calculate it, this tau. So it is the receiver clock error for which we are location. It is the reason why we are involving the 4 satellites. If I only want to know about the 3 coordinates ux, uy and uz, then 3 equations are sufficient. But I want to know about the receiver clock also. That's why we are saying that for a GPS receiver, it needs signal from minimum 4 satellites. So the 4 unknowns at the location of the GPS receiver related to the center of Earth and the clock offset, called as the clock bias in GPS terminology. So the receiver position is then referenced to the surface of the Earth and can be displayed as your latitude, longitude and elevation, and 4th one being the clock offset. So this clock bias value, which we had denoted by tau, it is found as a part of position location calculation process, and it can be added to the GPS receiver clock time to yield a time measurement. So the crystal oscillator, it needs to be highly stable over a period of few seconds. And the temperature changes cause the quartz or crystal, that is the frequency determining element, to expand or contract. So we need that it should be highly stable. So as I have mentioned that GPS satellites transmit the pseudorandom sequence. It transmit two codes, C by A and the P by codes, which are modulated at different frequencies. So this P code, now it will be transmitted using BPSK modulation at L2 carrier frequency, and is also transmitted with BPSK modulation on L1. So P code is transmitted on L2 frequency and L1, both in frequencies, and on L1 it will be in phase quadrature with C by A code BPSK modulation. Now we'll see how this L1 and L2 signals are generated. Now see, so I have got a L1 signal. This shows then, firstly I have transmitted the L1 code. L1 code is in phase quadrature with this. This is the L1 band, this is your L2 band. I have C by A code, I have P code. And another thing I have is a navigation message. This message is also should be transmitted. So C by A code is transmitted. This is the C by A code. P code is also transmitted in phase quadrature. And for this, so I've got two output. First one is having P code, C by A code, navigation message on L1 frequency. Another is only having this P code. It is not having information about the C by A code. And obviously you need to involve this navigation message. It contains the information about the GPS receiver, your location, your timing. So C by A codes are, these are generally the 1023 bit gold codes, and a shift register can generate them. Like see in this, so if I need, it is a 1023 bit sequence. How will you generate it? It's just a random process. So for example, I have taken a XOR gate. We have just used the feedback taps. I have put a feedback tap on this bit D3. So this bit along with this bit, they will be XORed and it will be fed back to the input. So in this way, a random sequence will be generated, which is 1023 bit sequence. So we call it as a pseudo random sequence. You cannot just easily predict it. So the C by A code for a particular satellite is created with an algorithm with a unique identification number. So satellite with ID number, it has a C by A code, which is given by this formula G1 T into G2, where T plus 10I and is the clock period of the C by A code. So we call it as a gold code sequence. Now how will you just receive it? So see, when I will receive it, first I will receive the signal. I have to eliminate noise, so I'll just pass it through a low noise amplifier. I'll down convert it the frequency because it is in gigahertz. I'll down convert it. I'll use an IF amplifier. It will just give you the intermediate component. And after that, now I need to process it. So I have an analog signal. I'll just convert it to a digital form. Then I will process it with the help of DSP and your microprocessors. And will check, the microprocessor will check whether the information that you have received, it is intended for you. If it is for you, then microprocessor will give you the information that you must display this information, the navigation message. If the information is not intended for you, then it will in turn inform you that the code which you have received, it is not intended for you. So it shows the simplified block diagram of the C by A code GPS receiver. So the antenna is typically a circularly polarized patch antenna with an LNA mounted on PCB. And the conventional superhet receiver is used to generate the IF signal, and it is sampled using I and Q, that is in phase and quadrature phase components. Now the GPS receiver, how we acquire the signal? So GPS receiver must find the starting time of each of the unique C by A code for each of the 4 satellites. It is done by correlating the received signal with stored C by A codes in any direct sequence spectrum system. Usually the receiver will automatically select the 4 strongest signals. And if the geometry of the strongest signal is poor, the satellite, that is, it is close to it. So and the pseudo ranges are almost nearly equal. So the receiver may use the several weaker signals. And if the receiver is making a cold star, that cold star means without any information about the position of GPS satellites. So it will search all the 37 possible C by A codes until it can correlate with the one. So it is necessary that when you are transmitting the information, the receiver must get information about the satellite, GPS satellite. Another important thing is the key feature. Its key feature is the navigation message. It contains a large amount of information that is used by GPS receivers to optimize the equation of satellite signals and calculate position. So it is sent at 50 bit per second by BPSK modulation. Now this GPS navigation message, it contains several information. So the complete navigation message is around 1500 bits. It will be sent as a 30-second frame with 5 subframes, and some information is contained in sequence of frames, and the complete data set requires 12.5 minutes for transmission. So that means these subframes, they are carrying a large amount of information. So the subframe will contain the information related to the satellite clock time data, orbital ephemeris, the satellites, its neighbors, various correction factors, the position of satellite will be updated. So see, this shows that we have got the information in header. Header will be having the information related to telemetry message, health of the satellite, how all the components are working, handover. Then we have got 5 subframes. Subframe 1, it will be containing information related to satellite clock correction data, age of the transmitted data when you have transmitted it. Subframe 2 and 3 are carrying the ephemeris of the satellite, because it is nothing but a lookup table for the satellite, which is where I am just updating the information for related to the orbital position of satellite. Then subframe 4 and 5, they are the LNAC data for satellites 25 and higher, and the subframe 5 is for the satellites 1 to 24, their health data. So these subframes 1, 2, 3, they repeat all data every 30 seconds, and subframes 4 and 5 repeat every 30 seconds, but transmission of this full data set requires 25 subframes over a period of 12.5 minutes. So that means it will take around 12.5 minutes to transmit complete GPS navigation message. So this was all about the location principle and how you will locate a GPS target, a target receiver, and what all information it will be requiring. So satellites, they are transmitting the information, they are transmitting it on 2 frequency bands, L1 and L2. It is coded by several codes, P code, C by A codes. Then you are encrypting the P codes known as the Y codes. The receiver will get signals from the 4 satellites. If the satellite, it is not getting a strong signal, then it has to look for a weaker signal. So whenever it has received the signal, it will just get the information, it will try to decode it. If the information matches, that means the information is intended for you. Otherwise, the processor will reject that information. So this is all about the GPS location. If you have got any doubt, then you can contact me. Thank you.